the Chancellor, His Excellency Dr. Thabo Mbeki, the Vice Chancellor and Principal of the University of South Africa, Professor Puleng Linkabula, to the professor that we are inaugurating this afternoon towards the evening, Professor Simiso Dube, her family members, friends, loved ones, members of the College of Science, Engineering and Technology, the management staff there, the executive dean who's actually across the seas, Professor Mamba, we see you, academic and administrative staff, UNISA students and visiting students from other higher education institutions, supporters, funders, UNISA alumni, distinguished guests, and again, Prof. Dube, the celebrity of the day, Sawubona, Sanbonan, Molweni, Dumelang, Afshen, Huena, good evening, Jambo. I acknowledge all protocol. My name is Professor Tenjiwe Meyiwa. I'm the Vice Principal responsible for research, postgraduate studies, innovation, and commercialization at the University of South Africa. Ladies and gentlemen, colleagues, I warmly welcome you to this inaugural lecture by Prof. Simi Dube. She's the Acting Executive Dean of the College of Science, Engineering, and Technology. She's a Professor of Analytical Chemistry at that college, which is a college we also refer to as the Science Campus in Florida, and her professorial status has been recognized since January 2021. Prof. Dube's scholarship focuses on developing greener analytical chemistry for food, safety, water, and environmental application. We also welcome Professor Roger Smith of the Department of Chemistry at a university in the UK, the University of Loughborough. Professor Smith serves as a respondent during this installation. We thank you, Prof. Smith, for heeding our call. In these challenging, turbulent times, which everyone will attest we're going through at a global level, the relevance of the work that Prof. Dube is about to share with us cannot be underestimated. If anything, it is at the center of what we should all be concentrating on. I don't want to spoil this lecture. She will go more into details about it. But for us as a university, contributing to the kind of scholarship, practically, but also with all other forms of resources, is a service to humanity. It is the way that we express our mantra as a university that shapes futures. Hence the importance of the content of this inaugural address that we are due to listen to. As an institution, while we are bound to produce good research, quality research, we equally expect those producers of this research, of that research, to have walked the path with mentees who are postgraduate students, but do so in attending to the sufferings, the injustices of our society, and do so being ready to actively participate in correcting the ills that our society, just like in this week in the news, we've had all the wrongs that continue to happen across the globe, despite us calling ourselves civil societies. Now, you will be asking, why is it important for me to make mention of this? It's because it is the good cadre of the professorate level of Prof. Dube's kind that we're able to respond to the ills that our societies and our communities face. It is for that reason, therefore, also that we take inaugural lectures very seriously, a zenith of all that we are about to be working with. It is this moment of expressing and showcasing this kind of research expertise that we want to become more real to the challenges that we face as a country, a continent, and the globe. You'll therefore be asking, so what has this got to do with being a full professor? Indeed, it does. Full professors whom we inaugurate through such inaugural lectures are recipients of awards. They serve as reviewers of other people's work. They lead research projects. They mentor upcoming emerging professors and academics. They mentor students. So they produce and reproduce research, produce and reproduce themselves. So I am requesting and imploring that through your chat box, you put comments of not only congratulating Prof. Dube with this installation, but also of giving her some ideas that may at surface value look pedestrian, but that could assist from your experiences on how to attend to the ills from the analytical chemistry point of view of the work that she's about to share with us. Professor Dube's response to the challenges to which I've made reference through this lecture, she's entitled it, A Journey Towards Green Analytical Chemistry.
Good afternoon, ladies and gentlemen. Let me welcome you all to this inaugural lecture by Professor Simiso Dube. But first of all, let me welcome the acting Vice Chancellor for this inaugural lecture, Professor Tenjiwe Meiwa, who is the Vice Principal, Research, Postgraduate Studies, Innovation and Commercialization. I also would like to welcome the respondent, Professor Roger Smith, who is the Emeritus Professor in Analytical Chemistry from the Department of Chemistry, Loughborough University in the United Kingdom. And I also want to welcome the entire CSET community, the executive and the management. I would like to welcome also the friends and collaborators of Professor Dube who are present among ourselves. I also want to welcome the family of Professor Dube. In particular, I would like to welcome her husband, Professor Nindi, who is present with us, as well as the relatives of Professor Dube, for the support that they have given to her until where she is at the moment. Ladies and gentlemen, before I call upon Professor Dube to give her inaugural lecture, I want to read you a profile so that you understand who Professor Dube is. Professor Simiso Dube holds a substantive position as a full professor in the Department of Chemistry. She was seconded to Head of Teaching and Learning in 2016 and is currently the Acting Executive Dean in the College of Science, Engineering and Technology, that is CSET. She obtained her first degree, an Honours Bachelor of Technology in Applied Chemistry and Chemical Technology from the University of Zimbabwe. She received an MSc in Analytical Chemistry and Instrumentation in 1998, as well as a PhD in Analytical Chemistry in 2001 from Loughborough University in the United Kingdom. She then joined the National University of Science and Technology in Zimbabwe in 2002 as a lecturer and was later appointed as a senior lecturer of analytical chemistry in the Department of Chemistry at the University of South Africa, UNISA, in 2007. Her research focus is on green analytical chemistry methods, spanning from separation techniques typified by electrically driven miniaturized systems, to micro-extraction sample preparation methods. These methods are advantageous in that they reduce the usage of toxic organic solvents and are therefore environmentally friendly. In recent years, she has developed great interest in nanomaterials for the removal of emerging pollutants from water, medical application, as well as analytical work. Other research focus includes developing and validating analytical separation methods for traditional medicine, thus providing quality control protocols on this in the market. Professor Dube has supervised to completion 25 postgraduate students, that is 13 masters and 12 PhDs, and published 39 journal articles, 1 book chapter, and 2 accredited conference proceedings. She has sourced external funding for research, teaching, and learning in the amount of more than 11 million rands. She's a member of several professional bodies such as the South African Toxicology and Chemical Institute, Society of Environmental Toxicology and Chemistry, American Society of Mass Spectroscopy, and African Network of Analytical Chemistry, among others, and has served as an external examiner for other institutions and a reviewer for scientific journals. Her research work has been cited for 739 times as per Google Scholar. Ladies and gentlemen, it is my pleasure now to welcome Professor Simiso Dube to give her inaugural lecture entitled A Journey Towards Green Analytical Chemistry.
Good afternoon. Thank you for this opportunity. I would like to thank the University of South Africa, to Professor Linkabula, the Vice Chancellor of the institution, to Professor Meiwa, who is the VP for Research, Postgraduate Studies, Innovation and Commercialization. I also acknowledge Professor Mamba, who is the Executive Dean for the College of Science, Engineering and Technology. I also would like to acknowledge Professor Roger M. Smith, who is my respondent today as an emeritus professor in analytical chemistry from Loughborough University. I take this opportunity as a great honor for me to speak to all of you, and I acknowledge in the midst, of course, the friends and family that have actually joined and the colleagues at large. I decided to share with you what I've termed a journey towards green analytical chemistry. And as a professor in the Department of Chemistry, this is important for me because it has taken a journey for me to actually to get to this point. So without taking much of your time, my first reflection that I want to make is about the problems that we as analytical chemists are trying to solve. So what are we seeking to solve? If you look at the pictures that I've shown here, they are pictures that you should be very familiar with. If you look at the top there, we've got chickens. We all eat chickens, I believe. But then in rearing of these animals or chickens, we actually see congestion, which then tells us that there will be an outbreak of some disease or so. So for us to actually ensure productivity and food security, we have to use some veterinary drugs to manage some of the diseases that actually can outbreak. So those are the challenges that we have, that yes, we provide with the solution of veterinary drugs, but we don't want any of the residues to be found in the food that is then consumed. At the bottom, of course, you see there are vegetables, beautiful vegetables, and the fruits as well. But with that, also in the food industry, you're actually looking at pesticides. For us to actually have sustainable provision, we actually then use pesticides, and there's limited amounts of the pesticides that should then be allowed in the food. So if we don't actually look at what happens to the food that we provide, then we have challenges, as you have seen in the past, where people actually get food
poisoning from different, whether it's pathological matters or it's related to the chemical contamination. Water is also a very scarce commodity globally, and wastewater pollution, or water pollution rather, is actually becoming a challenge. Most of our water bodies are contaminated with either industrial waste, but nowadays we talk of emerging contaminants, of which the drugs or the tablets that you see at the bottom here, they end up being discharged into the water, contaminating the water, and then we actually end up having issues of drug-resistant genes coming, which we actually struggle to curb as we try to manage this. So it is very important for us then to come up with methodologies that will actually give us, capabilities to detect the pollutants in water at very low concentrations. The thermal power stations, or the examples of the ESCOMs that we have, the power stations are good because we have to have power, but the problem is we also have some of the contaminants or the pollution that comes from there. The list is long, I cannot cover everything, but this is just to remind you where we are and maybe to see how one's work has actually been falling around, is actually been coined around solving these problems. So as an analytical chemist, we have processes that we follow. So we would then sample whether it's the vegetables or it's the meat or it's the soil from the power stations or the water. That's the sampling. We've got sampling protocols. Then there's sample preparation that then follows. And then there's an analytical method that then has to happen. With the analytical method for today, I want to focus on the separation because I'm a chromatographer or a separation scientist rather. Then of course we have to do the detection of the analytes and then the data analysis. For the talk today, I will focus mainly on the sample preparation and also on the separation methodologies. So as we solve problems, we're actually trying to solve them without creating another issue to the environment, hence the green in the approach. So green chemistry principles are principles that were introduced a long time ago in the 1970s, but there are about 12 of them, so I'll focus on just a few that I actually want to respond that is analytical. How then do we respond to these? So the green chemistry principle will then say we have to prevent waste. And then how do we as analytical chemistry prevent waste? We can actually consider replacing toxic reagents with innocuous ones. We can also, the principle can actually, or advocates rather, for designing less hazardous chemical synthesis, of which we can also in chemistry, analytical chemistry, use less hazardous processes. We talk about safer chemicals and products. Yes, we can explore safer reagents, safer solvents and reactions, and then in the analytical side, we use green solvents where possible. If we can actually decrease the usage of energy or have increase in the energy efficiency, so we consume less energy for our processes. There is also the use of renewable stock and so forth. So there are things that we can actually do in our own spaces, which actually can, bring or actually respond to environmental issues as we actually try to solve some of the problems that we have. So the use of reagents, solvents that actually can be obtained from renewable sources rather, and then the use of degradable reagents is another solution. And of course, if you really don't want this problem at all to eliminate, you then do your analysis in real time and prevent pollution completely. That means when you use remote sensing, where you go straight to the environment and then you do the analysis in that, so you can actually do remote sensing with that. So what then are the main strategies of green chemistry? We look at miniaturization. So miniaturization is actually looking at the reduction of sample and reagent that is being consumed, or minimizing, minimization of the waste and the risks thereof. Automation also is good because it reduces the consumes that actually are there. It reduces on the risk also for the analyst, because the analyst is not exposed to the hazardous chemicals. And then we can talk of online detoxification as well. So one, having said I'm a separation scientist, so when one talks of separation science for this particular talk, I will start by looking at chromatographic separation, and this talk will then focus only on the liquid chromatography, which is high performance liquid chromatography. So of course, chromatography, maybe there are young people at school there that have heard of the term, of course, it's a very old technique, but what I want to just briefly for the audience that is here to explain is that the principle really is looking at your analytes. So what we want to know about whether it's your veterinary drugs, we call them analytes. So they're actually introduced into a column, of which the column at the side they have given you pictures. That's a HPLC columns. Then the column will have inside some stationary phase, like packing that we actually use in the columns. So the analyte is supposed then to, as it moves, as we actually introduce some mobile phase, it actually then interacts with the stationary phase, and then also partition between the stationary phase and the mobile phase. As it does that, it is carried along, and then it gets to the detector where we can then see that. So we then see these peaks as different compounds now separated from a mixture. Then we can quantify and say how much of this is in the sample. But the challenge with the that we have faced long back, of course things have developed, is that in the HPLC mode you'll be looking at large volumes of organic solvents. For instance, you can actually talk about acetonitrile, which is very toxic and it's a carcinogenic solvent. So in that manner, you're actually generating a lot of waste that you can not manage. So for instance, you can easily get to about, in a year, for just one run, depending on your flow rate, to a very large 240, above 200 liters of solvents that can be consumed in a year for just maybe one type of an analysis. So because of that, it actually then does not actually respond to the greenness that we want. So yes, there's been development. Even now, we've now talk of UPLC, which is the ultra, where we are using very small particle sizes in the columns, so that we have fast separation, we've got low, we reduce in terms of the volumes of the solvents that are actually being used. So this made me then to move, sorry, I've moved my slides fast, to an electrically driven separation techniques. These electrically driven separation techniques are no longer the ones where we are actually using pumps. In the previous method, we are using pumps to pump the solvent. Here, we have high voltage that you are applying across a capillary. So the brown, there is the capillary that is immersed in the buffer. You've got your electrodes, then you apply high voltage. So as then you've introduced your sample, then when you're actually separating, your charged analytes are then dragged, or they are pulled with what we call the electroosmotic flow towards the detector, when we can then see them as peaks coming out. So you are separating analytes using the charge to mass ratio, but also you can actually see here in the diagram that there are some that might be negatively charged going towards the positive electrode, but because of the strong electroosmotic flow, you can then drag everything towards the detector. The only limitation is that if you've got neutral compounds, they are also just going to come as one peak, so you can't separate those. There is that limitation. But the beauty of electrical driven separations is that they are very efficient. So you are looking at very high efficiencies, and then high efficiency speaks of the capability of separating so many analytes within a very short space of time. So complex mixtures can be separated, and you can then quantify your analytes much easier. And this came about because of the limitations of chromatographic separations, where we couldn't actually separate enantiomers, so compounds that are very similar, or you've got what we call a chiral structure center, so you couldn't separate those. And then now with the electrical driven systems, you could then separate that. You could actually utilize this in the drug discovery, in genomics as well. So in terms of the protein size and so forth. But what is beautiful about the beauty of this method is that you can have a solvent reduction. So it's like there's no solvent consumption with the method. It is non-existent, because if you look at the internal diameter, my apologies, that is supposed to be 50 micrometers, not liters. So it's very tiny. And then the centimeters, you are looking at maybe roughly 50 centimeters, of which, if you really calculate the volume, we'll be actually looking at 5 microliter volumes, which is very, very tiny compared to the other systems that we've been talking about. So, of course, this had its own limitation in terms of has its own limitation when it comes to neutral compounds. So we have then different types, other types of electrical driven systems that then came for specifically to attend to the issue of neutral compounds. How then do you separate the neutral compounds as well? So that's where we have seen the micellar capillary electrophoresis coming by, where actually we have the analytes actually now interacting with the micelles. So you use surfactants, and these surfactants actually can form what we call a pseudo stationary phase. So your neutral analytes together with the other charged analytes can then be separated, which is what was a limitation for the capillary zone electrophoresis. Beyond that, in terms of developing, going in separating the analytes, even neutral analytes in a better way, we started seeing capillary electrochromatography. And this was now a hybrid between the high performance liquid chromatography and the capillary electrophoresis. Both of these techniques have got benefits. So the high efficiencies that are brought by the electrical driven systems mean that this technique has got very high efficiencies. You can actually achieve more separation, but also the selectivity now that you're bringing different types of stationary phases, so you can able to manipulate and then get to the selectivity that you want, and then you can actually have neutral compounds separated as well. I'm talking about that because it's a reflection of where one has come from. When one was still a student a long time ago, that was instilled of trying to come with green methods. So separation, we've done that in the separation of sulfonamides a long time ago. You've used the micellar method, that is the micellar capillary electrophoresis method as well in the past, and then we've actually been successful with the even open tubular electrochromatography for the acid and basic compounds. So this is a reflection of the separation technologies. Now, going forward with the separational technologies, you'll find that as analytical chemists, since I said separation, you might find that with the work that we are now doing, some will use that type of technique for us to reduce the solvents. Some, of course, there's been improvement in the HPLC that allows us to use lesser solvents, so we can still use that. But then still now, one then wants to go back to the sample preparation. What is happening in the sample preparation? So sample preparation has been a challenge, because if you actually working with sample preparation, you need to make sure that you're actually extracting your analytes in an efficient way so that you can actually present them to the analytical method that you are going to use, if it is separation. So this is a very critical step also in your process, and if things go wrong, then you actually have messed up your analysis. So in this particular slide, I'm just reflecting on the conventional liquid-liquid extraction. So in the past, you used to actually have, even right now, people actually using this. You have funnels, separation funnels, where you will have your two immiscible solvents, your organic solvents and your aqueous solvents. So your solvent, the aqueous solvent might be containing your analyte, which is your antibiotics or your pesticides that you have actually managed to extract and get them into an aqueous solution. So now you want to have a transfer of your analyte from one phase to the other. So this will require people to shake and then you get your analyte migrating from one phase to the other, and then you actually then, after the transfer, you can actually drain the one that you are not interested in, then pre-concentrate the solution, the solvent that then has your analytes. But you have to do this repeatedly to get good efficiencies. And then after that, you then have large volumes, which you then still have to actually heat up and evaporate, to reduce it and pre-concentrate. So these are the challenges that we had with the conventional method. So what other drawbacks do we see? So it generates large volumes of toxic hazardous organic waste, which is a problem, which is contrary to what we want in our principles of green chemistry. And then to dispose of organic solvents is also costly. It is time consuming. Yes, you may actually have shakers and try to automate, but it is very difficult to do so. Then also the other drawback is that it yields small sample to extractant phase volume ratios, which also translate to insufficient enrichment factors. So that is actually another drawback that we actually see with this method. So obviously there is need to minimize solvent consumption, and then there is need to explore biodegradable and environmentally benign extractant phases, which is where then the green sample preparation approaches are coming in. So these ones, I'll quickly go through them because we are not using all of those. People will use microwave assistant extraction, ultrasound, supercritical fluid. We have groups that work on pressurized water, solid phase extraction, and then the micro extraction. My talk today is interested in the micro extraction, and specifically the liquid phase micro extraction. So these come in different forms. People have worked on single drop micro extraction, which I'm not going to talk about. There is hollow fiber liquid phase extraction that we actually also, some of our students have worked with in the sample preparation. But for today's talk, I really want to focus on dispersive liquid extraction, just because of the time limitation that one has. So when we look at dispersive liquid extraction, this is an image that I'm showing at the top here, which typifies a schematic for how you will carry a dispersive liquid extraction. So take, for instance, if we've got emerging pollutants in water, that will be your water sample. In the vial is just a conical shaped vial, which then in that you can actually add salt if you need to actually look at the salting or balance the electrolytes. But the important part is that you actually have to add an organic solvent, a mixture of organic solvents, the extractant, and what we call the disperser. So in this case, we have something like acetonitrile being the disperser, chlorinated carbon, chlorinated hydrocarbon, carbons, which actually be carbonated solvents, will actually be the extractants. And then from there, you then introduce this mixture very fast with a syringe to your sample, and then immediately you start seeing you start seeing a cloud formation. In that cloud, actually the dispersion is actually taking place. So your analytes are being dispersed into these micro droplets. So there's several extractions in a way that are then your analytes are being transferred into those droplets. After that process, you then have to then separate the phase, your aqueous and your organic. So by centrifuging, you can then have at the bottom your sediment that is formed, and then you take it and then you introduce it to your instrument, be it an HPLC or capillary electrophoresis method. So when this method was introduced by Raze and colleagues in 2006, it was specifically for neutral compounds or hydrophobic compounds, and then also it was for water samples as well. So we had actually to explore this particular work in our group for other types of analytes, for charge analytes, because antibiotics, veterinary drugs, not all of them are neutral, but also for solid samples like your meat, your vegetables, and so forth. So we pushed this method towards that. This was the focus of then the work that we've done. So with the dispersive liquid microextraction, what are the appealing characteristics then? You will see then the organic solvent volume is very, very small. So you've reduced it drastically to microliters. So you are no longer talking about generating liters of waste. There is no waste, especially in this type of a method. So it is actually easy to operate. It is very cheap because the material that you're actually buying there is just your conical, your sample vials, which are actually very affordable. It is has got high enrichment factors, and then the extracts that you get at the end, they are quite clean and they can then be taken to the instrument for your analysis. So it is an appealing method, green method that we actually see. What have we done in our own laboratories related to this work? We have worked on the dispersive liquid microextraction, specifically for food analysis and water analysis. So starting with the food, the person that you see in the picture there is Dr. Moyema, who is now in the Department of Chemistry as a lecturer. She, in a work for a PhD, she looked at at how she can actually develop this green method to extract fluoroquinolones in food. As I said, fluoroquinolones are found in food for the reasons that we use them as veterinary drugs, but then we want actually to determine if then after we actually slaughter, or when we slaughter, we would allow time for those to actually drugs to have been reduced in the animal meat to a certain level. So in her method that she developed, under optimum conditions, of course, we see that she used, even if trichloromethane is seen as a toxic solvent, she managed to actually extract using just 200 microliters, very, very small volumes, as extraction solvent, just a ml of acetonitrile as a disperser. And then with that method, she managed to actually get recoveries with this method of 83 to 100% or 102%. And of the samples that we had collected from the market, she managed to determine that 75 of these samples had enrofloxacin, which was one of the fluoroquinolones, and then 12% contained about 4 of the fluoroquinolones that were there, that were being picked. So you can see the chromatograms that are shown here. This was done on HPLC, that, this bottom chromatogram shows, the samples that were picked from the market having some of these compounds. So that proved to be a good, efficient and simple pre-concentration and clean-up method for these quinolones that we're talking about. Another work that we've done, still in food, is with the tetracyclines. So the tetracyclines in beef, and this is work that was done in Botswana. Botswana is big for exporting beef to the EU, so they have to follow their standards. And so here we were developing a method which we will then compare with the standard method that they were using. So in this particular method, the person that is there is Mr. Sandy Moakansa, who was actually working on his master's qualification at that point, but now he's working on his PhD. So now with this, also under optimum conditions, because remember these are charged analytes, you have to play around with your pH. So he actually managed to actually get to the place where the analytes, all of them, can then be extracted efficiently. And then with 200 microliters of dichloromethane, so we see reduction of the solvent, just 1 ml of methanol as well. And the recovery is also a very good 80 to 105, which is acceptable. And then also, when he did real samples, he found that 2 of the tetracyclines were actually present in the meat that is actually being exported. However, the presence of the 2 analytes or the 2 tetracyclines, the levels, or when we are quantifying, we find that these were lower than the maximum residue levels that are actually allowable. So that means that the meat is actually fit for consumption. The traces or the residues that are remaining are not of a problem. So he also then compared, since this was a new method, with a standard method, and found that the performance of this method, especially the accuracy, the precision, was the same with the one that they had in their own protocols within their same within their environment. So that is one of them. We've done different things. I spoke about maybe options of completely eliminating or organic solvents, or in other cases where you reduce the organic solvents as far as possible, or bring in other content that can actually, or solvents that can actually enhance the transfer of the analyte from one phase to the other. So for instance, Dineo, again, in the same work, she actually also expanded the work and explored using different surfactants to assist the dispersive liquid-liquid extraction. So she actually then had to use just mostly the surfactants, topo, which is a neutral, alicate, which is actually a charged surfactant, which then she actually used to still, try to extract fluoroquinolones using still the protocol of the DLLME, and then successfully did so. And also on the left we have now Dr. Buze Tadese Negusi, who is actually from Ethiopia. He worked also on the multi-class pesticide residues in the fruit and the vegetables. Also, in this case, he also tried to limit the use of solvents, that is before getting to the DLNME. So he actually started by treating the solvent, the samples with combining acetone-based, salting out, assisted extraction, and then after that doing dispersive, so that even the preliminary step before DLLME is also green. So these are the examples that we actually have. And then of course with ionic liquids actually can be then solvents that then you substitute to completely remove the dichloromethane in the extraction. These have low volatility, they are tunable, viscosity, and they've got electrolyte conductivity. So we have started working in this space. Preliminary, there's a student whose work will actually come soon. He's working on the extraction of DLLME of the anthelmintic drugs, 20 of them, and using studying different ionic liquids for that. So coming to another shift, maybe before I step, of course, we've got fabric sorptive extraction, which I won't talk about, but that's another work that we're doing for another PhD student, trying also to use very simple and very simple and fast methods for extraction, but because of time, I'll skip it for today. But if we look then at the shift now, that was separation and the analysis that one had. We've had also interest in nanomaterials. So my interest in the nanomaterials, still going on the green, is not to use synthetic polymers per se, but to look at the biopolymers as nano fibers for medical and environmental applications. Biopolymers are attractive because they are biodegradable, unlike the synthetic ones that you might actually have challenges with. And this work also is linked to the other work that you see on the screen of emerging contaminants or in water, because in this particular work we are actually looking at the occurrence of pharmaceuticals and personal care products in water, in which we have to actually, yes, we detect them in our water bodies, but then what? So we were coming up with the nanofibers as a way of finding material that can be used to remove then these contaminants once we have found them. So yes, it's sufficient for us to have analytical methods to detect what is in the water systems, but we need to move forward and then come up with protocols to assist in the removal. So I'll start first with the protein which is coming from silk. Silk proteins are of quite interest. Everyone wears silk scarves, which are very expensive, but what one wants to talk about is that silk is actually a natural protein fiber that is actually produced either by silkworms or spiders, scorpions, and flies, and so forth. So as they actually form those webs, they're actually making some form of protection around themselves, the spider webs or the cocoons that we then, in this form, in the case of silk worms, are shown at the top there, where you are having cocoons for the moth then to actually be protected. So if we look at the silkworm cocoons, they've got two types of protein, what we call fibrin and sericin. So 70 to 80% of the cocoon silk thread is the fibrin, while about up to 30% is the sericin. Sericin has got very good biological properties such as the biodegradability, biocompatibility, and the moisture retention capacity. Hence, you see their products for your facial products which actually have got sericin. So there's quite a lot of lotions, facial products that actually have sericin. On the other hand, the fibrin has very outstanding mechanical strength, and it has got high thermal stability, and it is biodegradable. So this is also making it attractive. The biodegradability is attractive, and we've seen it actually being applied in sutures, or that is your wound dressing, and also tissue engineering, and then drug delivery in the medical field. So for us then, how then do we take the biopolymers and then we make them into material that we can use? We use electrospinning. Electrospinning is a method where we will then take the polymer into solution. We apply a field across the tip and the collector, and then as we actually pump through a syringe, then there is fibers that then get collected, but they actually form in nano size, which is giving us high efficiency, high surface areas, and so forth. So the application is quite good for that. So looking at then the work that we have done on the cocoons, we have actually looked at the electrospinning of silk fibrin, nanofibers. The silk fibrin was actually electrospun. We characterized that, and this is Dr. Muka, who has worked on this particular project. From the work that we've actually done, the chemical characterization of the locally found species was actually done, giving us the type of material that we have and where it can be applied in terms of its crystallinity. And then from the work that we've done, we've shown that it is amorphous, but you can treat it and improve the crystallinity using some thermal treatment. And then from there, she actually tried to, she had to blend the biopolymer with the PVA, because you need some viscosity to carry that particular polymer. So in that work, we actually managed to fabricate then the nanofibers, which were then used to develop some wound dressing, which she then tested in a PhD work. The other work that is related to the silk is the one that was done by soon-to-be Dr. Homo Hlobisile, where she actually had to look at the ones from Swaziland, which actually are very, the cocoons are very hard to dissolve. So she had to develop dissolution protocols with the interest of then making a nanofibers out of this. So she successfully managed to do the nanofibers, and also in a case she also did the films out of that. And then from the work you can see the diameters, the average diameter is in the nano range, and these are the same the mats that she actually found, the fibers showing that she actually has that type of a nanofiber. But the application then thereof, which she was interested in this particular work, was for the removal of emerging contaminants in water. So that she's actually used it in that area. Again, with the silk proteins, we've had also another angle of interest now looking at the sericin. The sericin is the work that also soon to be Dr. Manessa, who is in the chemistry department as well, looked at the fabrication and characterization of the sericin blended with PVA, and with him he had to form the composites, and looked at different species that we have, and with an intention of actually applying them as a biomaterial. So he was looking at the antioxidant characteristics of this material, looking at the cytotoxicity and so forth. So this is the actual work, and also characterize the structure of the sericin as well, the crystallinity, but coming to a conclusion that the material is actually amorphous, and it is very bioactive and It's a good antioxidant rather. So with that, then we looked at also the chitosan material. So chitosan can also give you some biopolymer that you can use to form nanofibers. All the biopolymers that we've used, we've had to use PVA. PVA, because it's biodegradable, for that reason we've then blend that and then we electrospin. So the mat there is a nanofiber that is being shown with 380 nanometers that actually found. And with this, we used it also for the removal of emerging pollutants in water. So in the work that she's done, she found in the optimum conditions that she could actually move most of the analytes. That was the naproxen, phenoproxen, diclofenac, and so forth. These were the acidic drugs that were in water. But when she was running it in the lab, of course, she would get 100% removal. But when you now actually take it to the real environment where there are other contaminants in the water, then you see a significant drop to about 40% for some of the analytes. Plant biopolymers, so I've been talking about the silk, but there are other plants that also have some proteins or polymers that we can actually use. And we've done that also in the lab with some of our students. And then here we're looking at moringa seeds. Moringa is a very common plant that people are using for medical use. So the moringa, you grind it, you actually extract the protein. You actually, after extraction and separation, you then take it to a freeze dryer. From there, you mix it with also PVA for the viscosity, and then you do the electrospinning and you get the mat. And Dr. Manesa, sorry, my apologies, is Dr. Kebede, who is actually has been a former PhD and a postdoc in the group, worked on the fabrication and characterization of the electrospan nanofibers from moringa, and successfully found that this material can then be used for different environmental applications. So the same images are showing that he managed to get 130 to 400 nanometers, and the morphology and the diameter of the nanofibers were mainly affected by the concentration, of course, of the blend. And then FTIR and the FT Raman characterization showed the functional groups to be mainly the amine and the amides that we actually have interest in terms of the removal of the analytes. And then, of course, further characterization was done using XRD, zeta potential, and so forth, confirming that the material has got an amorphous structure in it and is quite stable. And it is therefore a promising material for environmental water analysis. And these are the examples. For instance, he has used that in the removal of veterinary drugs in water. He's used that in the pharmaceutical, in the removal of pharmaceuticals. So very high efficiencies were actually, removal efficiencies were actually being obtained with this type of a material. And also the non-steroidal anti-inflammatory drugs, we've done work on that with the carbamazepine, and even then we find very high efficiencies, removal efficiencies. So in terms of the summary really for these types, all these, the non-steroidal, in the effluent, we managed to get removal from up to from about 70 to up to 95, 96% for the different types of the groups, which is a promising material. Also, anti-retroviral drugs, we've actually, and related drugs, we've actually explored those using the same material, but this type, a different plant. We used the Monday White, a different type of a plant protein, electrospinning again, and then we actually found that this material has also very good removal capabilities for ARVs. So with that, I would like to acknowledge the following. Of course, the institution of UNISAS, the University of South Africa, rather Department of Chemistry, for affording me the opportunity to explore the ideas. The Women in Research funding, where I had a 3-year grant to support some of the work that has just been presented. The Water Research Commission, the National Research Foundation for funding, and collaborators in the work. I've worked with Professor Nelson Toto while he was at Rhodes, and then he went while he was in Botswana, actually, then he went to Rhodes and then went to Bitri, and now he's in the government. And then Professor Nindi, who is working in the Department of Chemistry now at Inaugural. We've worked very collaboratively for some years, and the picture here, of course, is showing the postgraduate students that have in several ways contributed to the work. I could not touch all their projects, so I just have to mention that I only touched for a few examples of the students that I've shown here, but there are other focus areas that one has worked in and has interest in. So I appreciate all the postgraduate students, and there are some who have graduated and have gone. These are fellows from Ethiopia who were actually studying with us here at the Florida campus, and they'd gone back, so they had gone for their graduation, 4 PhDs, 3 PhDs, I'm now counting myself, 3 PhDs in that graduation event, which was a great excitement for us. So we actually have seen so much productivity in going into green chemistry. So it means then the way forward for green, yes, we still need to explore more methods that actually allow us to look after the environment, but find more solutions, as we actually want to address all the challenges that actually face us in our society. And with that, I would like to thank all of you, particularly the family members that have joined today from all over. I do appreciate you. I appreciate my friends that have also joined from all over. I recognize all of you, and I like to thank my colleagues at UNISA, in my college, and across the other colleges that have also participated. It's been a journey, and it's a journey that has not been on my own, but with all of you supporting. And I also want to appreciate in our midst my fellow family from my house of worship, led by the bishop and the congregation from Bible Life Ministries. And with that, I would like to thank you.
Thank you, Mr. Chairman, for your introduction. Good evening from Loughborough in England, and greetings to the senior members of the university, to Professor Dube, to the members of the university community, ladies and gentlemen. I'd like to start by thanking the university for the invitation to present the response to this interesting and informative lecture. Beginning, of course, by offering my congratulations to Professor Simiso Dube on her appointment to a chair in analytical chemistry. One of the pleasures of a university teacher is to see the career successes of your former research students and to discover how they have forged independent pathways to senior positions such as academic chairs or as leaders of industry. Simiso's lecture illustrated how her work has introduced a number of novel ways to reduce the impact of analytical chemistry on the environment. This field that she has chosen is important as we have reached the anthropogenic geological era in which the structure of the world has been changed by mankind through industrialization and resource depletion. The continuing impact of carbon dioxide and other gases, many created by solvents used in the analytical laboratory, can be seen in recent years. We've seen bushfires in southern Europe. We've seen flooding in Sydney, Australia. And this is all down to climate change and global warming, raising the average temperatures. In England, we've seen this last few weeks unprecedented temperatures around Loughborough. And in fact, this has resulted in some dramatic headlines. So Simiso has described how the role of an analytical chemist is not just to monitor the influence of mankind on the environment, but also to ensure that the work of the laboratory does not add to the problem. My connection to Simiso goes back to 1996, when she came to Loughborough as MSc student in analytical chemistry, and then continued on with me as a PhD student, continuing the same topic on electrochromatography. She worked in the laboratory together with a number of electrochemists and other analytical chemists, some of whom you see here. At least one of these has also gone onto a chair, and you can see her working at the bench. This work required considerable dexterity and patience. What she was trying to do was to take what has been the waste content or the waste generated by research laboratories in terms of liquid chromatography from one instrument could use as much as 500 litres of solvent a year. By simply reducing the diameter of the column, you can reduce this to something like, well, 2 or 3 litres a year. With electrochromatography, probably even down to microliters. This resulted in Simiso's first presentation at a conference in Greenwich in 1999. You can see her poster here. She's also taken this task further to improve analytical separation methods and analytical extraction methods in which you're trying to separate the analyte of interest from a matrix, which is something that will probably interfere with both the analysis stages and with the instrumentation. Originally, traditionally, you used organic solvents, usually organic solvents. These were very slow, time-consuming. Some manual operation requires usually 3 times extraction, taking 3 times as long. So one of the first things that Simiso had looked at in her work has been the dispersive liquid-liquid micro-extraction, in which a small volume of microliters of immiscible extraction solvent is introduced as a solution in a solvent, as it was sprayed in, and that effectively acts very efficiently, as she has shown in her work. She then went on to look at new extraction media, and these were very interesting because she's made use of natural materials that might otherwise go to waste. Things like silk cocoons, chitosome and seed proteins, parts of the plant or animals that would otherwise have to be wasted, would have to be disposed of, thereby also create waste. So her new extraction media have proved to be very efficient for extractions and then towards analytical chemistry stages. And she's also found it's useful to use these for cleanup, so that you can take and a good example of where that's valuable, both in monitoring and in cleanup, is in wastewater. Here is a display of some work that's been done recently in Europe, showing how drugs get carried through wastewater systems and out into the water supplies. These can produce problems with antibiotics, but also problems with recreational drugs. And in fact, there has been found to be a considerable increase in the number of drugs being used immediately after the end of a World Cup match. One of the other aspects of Simiso's work has been her work in the CNAC meetings, which brought together people from across the world to make presentations from the USA, from Canada, and from the UK, myself. And this was very good for the university because it encouraged research students and younger members to become directly involved, either in presenting lectures or more often in presenting posters, which can then be discussed with members of the staff and with other students. And this is a valuable introduction to many of students' lives. And she's been involved in a number of these, initially in Botswana. More recently, UNISA, I've visited her as a respondent at another inaugural lecture, as you see here, and also at the more recent SECI meeting, Society of South African Chemical Institute meeting, where I also talked on the subject of how to reduce pollution, because this is now a major problem. And in many ways, we've investigated other aspects, things like the use of superheated water, supercritical fluids like carbon dioxide, but we have to be careful there because they, again, can also produce contamination. So miniaturization has been an important factor, and this is the aspect on which she's working. I'd like to end by thanking you all for coming to listen to the lecture. I thank Simiso for the invitation to present a response to her lecture. Thanks to the university for accepting it, and to wish you all best wishes for the future. Thank you.
One, action. Wow, wasn't that impressive? Thank you, Prof. Dube. Thank you, Prof. Smith, for zooming us into what all this means through your response. In closing, I'll remind you that the chat box is there for congratulatory remarks, but also for give us questions, ideas, insights into what you could possibly do further in her research. Thanks to you, Prof. Dube, for an educational lecture. There is an acknowledgement of the extent of your scholarship and the societal significance of the focus of your research. Through this lecture and its analysis, we are certainly wiser than we were before we entered this hall and before we started this lecture. Thanks, Prof. Dube's family, for attending the lecture, more so on a weekday in the evening, and thanks to all the patrons of the lecture for gracing the lecture, and of course, without least, to thank Professor Smith for an extremely engaging response. Lastly, but not least, in importance, our colleagues that I want to especially express gratitude to for working behind the scenes, who never get to come to the podium because of much more harder work than the work that I'm doing right now. I want to single them out in this fashion because they ensure that the lectures that we present are of a high standard at institutional level as well as at various ambits. I refer to the Department of Institutional Advancement colleagues who've done all the work behind the scenes, the media, our internal media and external media, colleagues who've worked on the camera, photographing, the videoing of this work, IT, facilities, colleagues, and those that have prepared this venue and the food that we're about to have in the fashion that they've actually perfected it to be at an excellent state. And so is this venue. With all this said, we really have been fed well through this lecture. I thank you all for availing, and of course, our queen pin of the evening, Professor Dube. Thank you.